Okay, welcome to our final session of the day. Please welcome Tobias Goeschel with Domain-Driven Design and Cloud-Native Environments. Please give him a warm welcome.
Hi. Not sure this is on. Oh, yeah, now I can hear myself. Awesome. Maybe everybody should move up here a bit, because it feels like I'm talking to a large empty room, and that kind of makes me nervous. More nervous than I'm already because of giving a talk, anyway. Please. All right. So, well, maybe more people are coming in anyway. So I'm Tobias. I work for Amazon Web Services. I'm a solutions architect. I work with customers. I try to help them use our products so that they can be successful in some form. And I have a bit of a story to tell you. So I want to introduce you to a dear friend of mine. His name is Harry. Harry is this guy, the pretty regular bloke. He comes from an obscure country whose name I forgot. The particular thing about this country is they speak a lot of different languages. And Harry's traveling Germany, and he doesn't much care about German culture. He doesn't care much about the language. He doesn't care about the people, too. He's a pretty unfriendly guy, actually. And then this happens. He gets struck by lightning, pretty badly, actually. And then after that, everything's different because he wakes up in the same hotel room every day to relive the same day. Kind of like the movie Groundhog Day. Except this is different because in order to get out of that time loop, he has to learn German. Obviously, this is something that I worked on a couple of years back. It's a German learning course that I developed for Deutsche Welle. It was conceived by an agency here in Berlin called Freiberg B. It was a pretty big program, actually. Consisted of 100 episodes of recorded speech, like voice acting, along with graphics, like you saw before. Every episode had 4 different games with it, so you could repeat the content that you learned. There were 20 different game types, really complicated stuff, from simple puzzles to super drag-and-drop heavy fancy stuff. Different types for every episode. It was all configurable, really complicated. That whole thing was supposed to be available in 30 languages, including ones that go right to left, including ones that have Chinese characters and that sort of thing. So back in the day, that was pretty fancy, really. We also had a vocabulary trainer. So basically for all of the episodes, there were words that you could learn, you could repeat them, there was scoring, different stuff, all of that included. And to top all of that, it should have been fully editable for people that Deutsche Welle would hire who were native speakers to actually edit the content. So this thing started in 2009, and I don't know how many of you were around by that time, but the world was a bit different then. It was done in Flash. Does anybody remember that? I was once a real expert in Flash. Really got me places. Anyway, so this was just before Steve Jobs killed it, and we used that because it was really the thing that you went to when you wanted fancy content, right? So had vectorized fonts, it had vectorized graphics, it was really nice on the eyes. There was a lot of good integration with video and all that. So that's why Flash. Back then, Java was for the backend, running on JBoss, using MySQL database. There was an accessible version done with Apache Wicked. Does anybody remember that one? Back then, we rendered the HTML in the server, not in the client. Anyway, because this was all content, right? It was all CRUD-based. It was pretty obvious. Like, there were words, you could edit those, create, update, delete, the whole thing. There were different game types, same thing, right? Anytime there were changes, it was pretty obvious that this was a really simple application. And to make it more simple, I created myself a domain-specific language. Maybe some of you will remember how that worked. And software generators, right? So basically, we would create a language model and then write the structure of the application in that model and generate the code that should be executed. There were 4 developers when we started out, and for a couple of reasons, after 3 months, I was alone. But, there was still 1.5 years left. I had all those generators. What could go wrong, right? I thought, this is my big breakthrough. I'm going to save this project, and then I'm going to say, I built this. This is awesome. Obviously, that's exactly what happened. It turns out that in the beginning, we pitched only the learner application, right? So Deutsche Welle only saw the thing that the learners would see. And after about a year, we showed them the editor's application, and they hated it. And I was sitting next to them, and I could totally see why. Like, it didn't work at all. We could edit the words, but it turns out that some words are longer in some languages, and some have word wrapping in the wrong places, and then all the components are somewhere different, and nothing works anymore. So it wasn't good enough. Just editing the words wasn't good enough. It had to be positionable. They had to have some drag and drop stuff. They had to move stuff around in order to make it work. We redesigned the whole thing. About a year later, I realized that the generators didn't scale. They did all the middleware, they did all the data access layer, but it turns out that publishing content is actually much more complicated than CRUD. There was a publishing workflow. The editors were people that weren't trained, really. They were like students. They should be the ones editing the language, and when they hit publish, it shouldn't go live. Somebody would have to look that over, and then they'd have to resubmit for editing if there were any mistakes in there. So it turns out there was a really complicated business workflow behind this. Lo and behold, I had to rewrite the whole thing using DDD. That was painful, really painful. I also had to invent a subset of CSS for Flash in order to position all the elements for different languages. So in Arabic, you could say it's positioned at X 275 and at Y 57. That was pretty complicated. And there was more. I could go on. Anyway, this whole thing lasted until early 2014. But somehow the budget ran out in 2010. I ended up in a burnout with about 45,000 euros in debt, and I ended up quitting my self-owned business and getting a real job with these people. But it wasn't all for nothing, right? I learned something. I actually took away quite a bit of learning from that thing. Painful learning, but I did learn something. I actually don't need anybody else to screw up the code. I can do that all by myself. That was a really important learning, by the way. This is true for all of you. It's also much more important to listen to people and to talk to people than to focus on the tooling, right? All those generators won me nothing. I had to talk to the actual people involved in the process to find out that I was building the wrong thing. So, I made a decision. I quit the generators. I built everything anew. I moved them out of everything that I had built before that had any merit to it. And I decided to become an expert in the opposite, right? Instead of generating more code, I would focus on making it more simple. I would focus on crafting code, actually writing simple code, good code, and on DDD. Now, why am I telling you all this? Because that's why I'm here, right? In the end, that's how we ended up in this place. And this got me to join this company. I spent a couple of years as a consultant. I learned even more DDD. I learned event storming. I did a lot of workshops with customers. I became a real business person in terms of thinking, right? Always focused on customer success. And then eventually I thought, I want to go out in the real world, in the big world. I want to see what I can do with this. And I joined AWS. And this is where my story starts. Sorry for the long intro, right? But this is actually where we start out. I joined AWS, and it turns out I went from this to this. Everything's built with icons. I can still not tell you which one of them means which service. But it's really detailed, and it's always extremely precise, and people actually know what they're doing when they're building these things. But it is not my strong suit, not in a long shot. So I was thinking, I can go in and I can help these customers build really business applications. Nobody knows that at AWS. I can go in and just do it, right? And we can change the world there. I ended up talking about networking and CIDR blocks. Really not what I was used to. And that got me thinking, architecture always translates to technical stuff at AWS for some reason. And things are always different from what I expected before. Right? That everything changed. I was building regular business applications, company-sized business applications before, and now in the cloud everything is distributed. In the cloud everything is an API. In the cloud everything is built by consumption. That's different. Everything is a managed service. Ideally, we're looking for that. Everything is serverless. No scaling. Hey, it's all doing it by itself. Everything is automated and also secure. Doesn't everybody like the IAM policies on all the different parts? My favorite. So, that's me. About 2 months in, right? And I started wondering, I learned all these things, and I believe many of those things to be true still, right? They're true for the cloud as they are for everybody else. But how does it help me? How does it actually help me reason about all those moving parts that I'm now dealing with? Last year we did KanDDDinsky Open Space, and we ran a session. Should we apply the same logic that we apply to our regular code to infrastructure as code? It was a good session. So I started looking into things from the top down, right? And this is I hope the journey that we're going to do together now. Let's talk about boundaries. Favorite topic, right? Everybody always talk about bounded context. That's the most essential building part. Everything's built out of bounded context. They're so important, we actually form our companies around them. We build teams that match the bounded context. Why should that be any different in the cloud, right? Bounded contexts are defined by language. Language is still there in the cloud, pretty sure that. So this is all true still. How does it apply to the things that we're now talking about? Bounded contexts are a technical realization of a subdomain or a domain, right? One possible one. There could be different ones. They could also be partial, right? So several bounded contexts could make up one subdomain, but not the other way around, hopefully. Also, one team can own more than one bounded context, but a bounded context should never be owned by two teams. So same logic, right? Sadly, in reality, that's sometimes not the case, especially when you're dealing with legacy software or third-party products that somebody bought because they thought it was a good idea. How do we implement bounded contexts? Eric Evans says, use modules, build packages. Incidentally, so does Von Vernon. We also know that microservices should roughly be the size of one bounded context, right? Here I'm dealing with serverless. So what's different about serverless? Serverless components are built by consumption. You pay for what you use. So they shouldn't be running all the time. These other microservices, they're always on, right? You run them up on Kubernetes and they're idling by themselves somewhere. In the cloud, that actually costs a lot of money. They have to be stateless, because otherwise we couldn't shut them down. Latency is somehow important, right? So if you start a Lambda function, the first time it takes longer than it does the second time. This is pretty much how a serverless function on AWS works, right? So there's an init phase where everything's booted up. There's an extension that connects the function to the rest of AWS. Then there's a runtime that's initialized, and then the function is initialized, and that's frozen. And we can reuse that. So all the invocations that happen afterwards, they're built on that same state in the beginning. And then eventually, when there's a timeout reached and there's no further requests to that runtime, it gets shut down in the reverse order. This is the thing that you pay for. This is the stuff that actually makes up the time that it takes until the function executes. How does that actually apply to bounded context then? Scaling, right? All those runtimes have to come from somewhere, right? They have to be available at some point, or it will take longer. So we have different runtime behavior that we have to deal with. There's also parallelism. We should make them as small as possible, because obviously when they're small, we can scale at much more fine-grained levels, right? We don't have to scale the entire bounded context, but just one part, the one that actually needs scaling. And then they're also finished much sooner, so they actually don't cost as much. But then also, number of executions is important. So we also have to watch out for things not being too small, right? Sometimes it's better to have just one function doing 3 things. How to make that decision? How do we actually deal with all that stuff? Well, there's a couple of options. We could do one virtual private cloud per bounded context. That's, for everybody who doesn't know that, that's a virtual network, right? Basically, we pretend that it's your own data center. We could do that for every bounded context. An account can have more than one VPC. However, a couple of customers, actually quite a lot of them, will limit you to only one VPC per account, so that's not always an option. And VPC actually incur cost. So if you've heard about the famous network translation gateway, NAT gateway, and how that applies to your AWS bill, that's what I'm talking about. So outgoing network traffic, really expensive actually compared to other things. So how about one account per team, or one account per bounded context? That would work, right? That would be really separated. We could enforce those boundaries. That would be a good idea. In a regular company, getting an account is actually not that easy usually, right? So you can do that if you're all by yourself. That's quite fast. You can sign up for a new account in no time. But if you're working for a company that actually has to have consolidated billing in some form, somebody's going to have to say yes or no. So we have a pattern called the landing zone, or the account factory, that we use for that. So we help customers build automation for creating accounts so that people can do that in self-service. Without that, it's difficult. Because platforms are a dependency, if I have to ask for permission at some point, I have to have negotiation. Negotiation takes time. So now you're going to say, what about Kubernetes? I'm using Kubernetes. Isn't that the cloud? Yes, it is. Of course, it is. It's different, but it's still the cloud. One bounded context per deployment, maybe. But then you might have more for a subdomain, right? So that's not really a great match. One bounded context per namespace. That would be an option. How about one namespace per team? Right? That's clean separation. We can have more than one deployment in a namespace. That kind of works out. How about one cluster per team? How many people use Kubernetes? A lot, okay. How many people have more than one cluster in their company? Maybe half. You should do that more, right? These are managed services now. You don't have to maintain the cluster yourself. And it's actually quite easy to spin one up. What that will do is remove a platform. Right? If you have a single cluster for the company, you're always going to have some operations team that you have to ask for permission. Right. Enough about bounded context, let's talk about boundaries. One bounded context can never exist in isolation, usually. I mean, there's one exception, but usually they have to interact somehow, right? So there has to be some integration. And most of the time, we hear people talk a lot at these kinds of conferences about all of this stuff, right? The different ways that bounded contexts can interact with each other, context mapping. I'm not going to bother you with all the details, but just be sure there's different ways that they can relate to each other, and it's all about who depends on whom. An integration is equivalent to a contract. So anytime you integrate with a different bounded context, you have an agreement on how do we interact with each other. It's about forms of communication. What messages can I send you? And what will you understand? What will you respond? But it's also about social dynamics, right? Who do I have to ask if I want to change something? And it's also a team boundary. Context maps helps us to figure out how these should be built, right? So how the integration should work and how the nature of the integration should be enforced. I can implement an integration as a regular REST interface, for example, right? So there's somebody who's defining the interface and somebody else who's consuming it. I could do that with GraphQL. I could use remote process invocation. I could use messaging, domain events. All of that is a form of a contract. I can use OpenAPI or similar documentary items to make that explicit so that somebody can come and say, what does this interface give me? And they'll get an answer. And I can use consumer-driven contract tests to actually enforce that and make sure that it doesn't break. This is, incidentally, a variation of the ports and adapters pattern, also known as hexagonal architecture. It's just very high level. Right? We have a core of functionality inside of a bounded context, and we have interfaces at the border. So let's talk about boundaries. Earlier I said bounded context should be implemented as modules. Can small components have even smaller parts? Of course they can. Serverless functions have layers. How many people are using serverless anyway? Okay, maybe a fourth. How many people use layers? Not enough. Layers are much like package dependencies. They're binary dependencies, right? So this means coupling. Be aware of that. So, how does a serverless function usually work? We have an invocation source, somebody who's telling the function you should now run. They send an event and a context to the handler. The handler is the actual function. It'll execute on that event and then send a response, or not. Pretty simple. Inside of the function, it looks pretty much like this. So you're going to have a setup code in the beginning where you wire up all the dependencies on the moving parts, vendor specific usually. That's where you put in the dependency on your DynamoDB table if you're using that, for example. Then the Lambda handler will execute and well, the ones that I'm writing usually look like this. You have a try-catch block on the outside to make sure that you're not going to miss any errors. And then there's some sort of input validation. Does the event that just got in match my expectations? That's not domain validation, right? It's just, is the input correct? And then, if it's okay, then I'm going to call the domain stuff, and I'll get some sort of response. And if it's not okay, then I have error codes. And if I'm working against an API gateway, for example, those result in HTTP error codes, sorry. And if I'm working against a queue, for example, I could say that the processing failed, please retry. So it will very much depend on how I got into that handler, how I'm handling the output. So we have initialization, we have integration, the domain logic, and then we have more integration. Sort of like an onion thing. And if we translate that to layers, we have the Lambda itself, the module, that I cannot make more generic because it's integrated very much with the environment that it's running in. And I have imported stuff. That includes the domain core. I can isolate my domain core. I can actually test that in isolation, just like I would in a regular monolithic application. And I can have shared code, but beware of that one. In summary, Lambdas should wire dependencies, should take care of the event and error handling, and should issue responses. But they should only ever call the layers that have the actual domain logic. I actually said that before. You must only ever share the domain logic within the same bounded context. That's really important, right? You can have a domain core that spans more than one serverless function, but it shouldn't be shared by many teams because it's a dependency, and a binary one at that. If teams share layers, then they should only be technical. So something like security code, for example, or when you're integrating with Kafka, right? So all the stuff about technology, you can share that among teams. But again, beware, that's a dependency. If you over-index on don't repeat yourself, that's going to hurt you. It's going to slow you down because it means negotiation. Let's talk about boundaries. Fences make good neighbors, or so they say, right? Boundaries should be enforced. Teams should not share infrastructure. Infrastructure should always be code. And it should be integrated with the application that you're writing because it's really the same thing. Deployment pipelines are also infrastructure. You should not share them. How many people share a common deployment pipeline? Company Jenkins. Not so many, that's great. How many people have a deployment pipeline? Thank God. So, shared infrastructure has consequences. You're going to have side effects, right? So if you share the same Kubernetes environment, if one team manages to take down the server, then you're going to feel that, even if it's just waiting away the current load from your downed host. I actually dealt with a broken cluster a couple of days back. 1,000 teams working on a single Kubernetes cluster, that's not a lot of fun for the operations team, right? So blast radius, really important. Something goes wrong, you don't want to have to deal with your entire company being broken. You have the negotiation, again, right? You have to deal with other people. You have to make sure that your resources are used in some form. If you're only ever dealing with your own infrastructure, you don't have that need. And then if you build large-scale infrastructure for your entire company, there's YAML. And they're huge files, or even like, entire trees of files. And you do the broken thing where everybody puts all the deployment part in a single project apart from the actual implementation. So we should align our infrastructure with the bounded context. And even if that means going a different way or longer way to actually share a couple of addresses or URLs or something using outputs. Use infrastructure as actual code. How many people use Terraform? How many people use CDK? I like that. There's CDK for Terraform. You don't have to deal with that shit anymore, right? So actual code. Actual code can have variables. You can name them. You can use information hiding. You don't have to write everything explicitly into that configuration file. It actually has some nice functions like grant read permission, where you don't have to write the policy code, that's the horrid one. Use infrastructure as actual code. Avoid the dreaded deployment repository because distance, right? It's not included in the same project anymore. You can't verify that its integrity is still intact. Use your policies, your security policies, to enforce those boundaries. That's really important. Don't just allow all. But what about Kubernetes? Well, you can align Helm charts or deployment descriptors with your bounded context. You can use that same infrastructure as actual code to execute and deploy all that stuff to your environment and integrate with all the other components, because lo and behold, Kubernetes doesn't run by itself, right? There needs to be some other infrastructure too, databases and such. Prefer self-service at all costs. Like, don't ever depend on other people to service you if it doesn't have to be that way. Avoid the single point of failure. I said that before. Make sure you have separate clusters per team. And there's serverless containers. Maybe you don't have to worry about all those clusters anymore. Maybe it's enough to just say deploy. I can only recommend that. So, shared deployment pipelines, I said that before, are a dependency. And somehow that's bad, right? But at the same time, you will have some common functionality that will show up every time that somebody deploys something, and it really isn't a good idea that everybody maintains their own solution for it. So it's okay to have common libraries. It's not horribly wrong. But please extract those. Don't build them beforehand. I've seen so many customers build stuff for 2 years before somebody's actually using it, and then the first time they use it, they find out it's not a good match. Build stuff, make it run, and when I think, oh, there I am again. Okay, so build stuff, find out how it works, and when you found out, then extract those into common libraries. Don't enforce stuff as a standard. That's a really important one. It's a suggestion. It's an offer, right? Here's our common library. You don't have to build it yourself, but if you really want to build your own solution, you can. Self-service, again. Avoid gatekeeping. How many people have that one person in their company that always says no? Come on, it has to be more than that. Right? Usually those are named data protection officers or AppSec or... Of course, these people are important, and they usually have a good point in saying no. But there should be some way of self-servicing yourself around that problem. There had to be some way of making it easier for the teams to actually get to deployment. So let's talk about boundaries. Data. Data also needs context. Usually, I tend to think of data as 3 different categories, right? So we have the operational data that that's what our business application use every day in order to run. And then we have the analytical data. That's the stuff that's generated from the operational data and then transferred somewhere else so that business analysts can run analyses on it. And then there's the operationalized analytical data, which is kind of, coming full circle. Once the business analysts or the machine learning experts have figured out a good model, we have to use that somehow to actually inform our business applications again. Funny, but different kinds of data need different architectures. The operational data should avoid central data stores at all costs, right? Usually, my customers are enterprise customers, and they're always going to tell me about the single source of truth. Usually, that's a DB2 running on a mainframe somewhere. And that contains all the data. And it's usually really tightly coupled because somebody thought, oh, there's a table that has exactly the information that I need. I'm going to just pull that, rather than going through regular interfaces. So avoid that at all costs. Every part of the business application, every bounded context, should make their own choices about data storage. And they should enforce their own consistency and accept eventual consistency everywhere else. Duplication is okay. It's okay to copy data. You just have to make sure that eventually it has the same state. Now, which persistence mechanism should I be using? I think as of today, AWS has 14 or 15 different database types in its offering, and they all have different characteristics. Why should I use anything else than MySQL? Well, for structured data and for data that's already curated, like the stuff in the DB2, it's okay to use a relational database. If it's unstructured, or if you have queries that are basically just get by ID or get as a collection, then you probably want to use a NoSQL database. Key value store, document database. If you have high volume of searches, or you want to do high volume text search, you need a search engine, probably. And if you have machine signals, lots of IoT data coming in, then maybe you want a time series database. And finally, we've all been waiting for this one, right? If you want to do time projections, you want to scroll back in time, or you want to drill down into events and find out fine-grained what happened at what time, then an event store is probably a good idea. But you can make those choices based on what the bounded context does, even part of it. You can have 3 different databases in one bounded context, and it's not a problem, because those are all managed services nowadays. You don't have to use that one big DB2 for everything. Operational data in business applications has to be available. It has to be there. We want to work with this, right? We don't want to wait for half a day until the batch is processed. So latency is important. If we add a lot of different components together, then we're going to end up with long execution times, and maybe that's not so great for our user experience. We can use caches, but that adds complexity. We could also use in-memory databases. That's also a data store type that you could use. We could use CQRS. That's really a good idea, actually. You can implement that in many different ways. You can use the technical infrastructure. I talked yesterday, I think there was a talk today about people using DynamoDB for an event store. And there's technical events that DynamoDB issues, for example, that you could react to and update your read models. But then that's not very DDD style. Trade-offs, again. Rule of thumb, limit your writes to one instance, so you don't have to deal with parallel writes, right? Parallel writes are really bad. You don't want to deal with that. But you can have parallel reads, as many as you want, so that can scale to infinity. Analytical data is really just a read model. I don't know how long I took until I found that one out. Like, there's ETL pipelines and there's all kinds of big data infrastructure information if you go on the AWS website, for example. There's so many things about how you pump that data from this bucket into that bucket and how you transform it, but it's really just a read model. Complicated one, sophisticated one for sure, but it's really just a read model. So, what is it used for? Usually, there's business analysts that do the controlling, right? They need structured data. They need the DB2. They need a data warehouse. And there's data scientists, and they usually take everything that they can get in the rawest form possible. So it's unstructured. They want to discover the relationships. They want to discover what's there. They need a data lake. Both of them need the data from everywhere. The more they can get, the better. How many people have a single data lake in their company where everybody puts their data and then it dies there? I've seen that too many times, right? Huge infrastructure, no idea where the data came from and what it means. So usually, third, fourth project that signs on to the data lake, the people realize, oh, we need to have some meta information and we need to have data lineage. Where did it come from? Who originated it? And who do I have to ask if there's something wrong with it? So you add layers on top where you should really be scaling down. Data sets have to be accessible, so we have to govern the access too. Some people may be able to see personal data and credit card information, and other peoples are not allowed to. And it's really important that we enforce that. So there has to be some infrastructure to govern that as well. And it has to be documented, and there has to be some form of search. Right? If I'm looking for something that I don't know exactly where I can get it from, I have to have some way of finding it. Remember that platforms are a dependency. That single data lake is a bad idea. It's been a bad idea from the very beginning, but it's still a bad idea. It should be decentralized. And obviously, it should align with the bounded context. What a surprise. Every bounded context should have its own data set. And the team should be responsible for maintaining it. So the decision whether I want to structure that data, whether I want to deduplicate, whether I want to clean it up, whether I want to throw away some part of the data because it's not important, that should rest with the team. And then they should publish whatever they have to the rest of the company. Again, it should be a self-service, so I shouldn't have to ask that team if I can use the data. I should be able to do that automatically in some form. That requires a lot of extra work, and it's called data mesh. Maybe you've heard that before. This is the single most important discovery of the last 5 years, I can tell you that. This is what enables large-scale enterprises to deal with data. Everything else is going to end up in the same place that the big ball of mud did. So, when we're done with the analysis, we have to somehow find a way of putting that data back into the operations. We need that data for machine learning, for example, right? So data scientists discover a great way of making automated decisions, predicting outcomes or recognizing stuff from patterns. Then they're going to train their model with historical data. So we have to have a large data set of what happened in the past in order to train those algorithms. And then somehow those models have to find their way back into the operations so they can work on the new data that's coming in. That also is a team responsibility. Right? So there's a data science team that does all the research, but once it comes back, we have to take care of that. We have to understand how it works. That's really important, by the way. You can't leave that to data scientists only. And models incur drift. Right? So over time, they become less useful. Data changes. So we have to have a way of retraining the model every now and then, gathering new data, using that to do new training, honing the model, and then redeploying it. If you do that manually and if you ask the data scientists to do that, it's really slow, obviously. There's one data science team usually in the company, they have a lot to do. So you wait. And during that time, the model is not useful anymore. Also, people make mistakes. Who would have thought that, right? Automation is really important here. It's called MLOps if you want to search for that, right? But there's ways of doing this automatically in some form, at least. Maybe you have to push one button, but it doesn't have to be a data scientist doing that. Still, if you're not following Abiba yet, please do that. Machine learning is a slippery slope. It's useful, but it's also wrong. Even more so when you do everything automated, because nobody's actually looking at what's coming out of that. So let's talk about boundaries. One final time. Who's using low-code, no-code environments? One. I like that, actually. So, low-code environments promise you to get all the results for none of the work, right? Everybody can do it. You don't have to be a programmer. That's awesome. It's also wrong. Usually you have visual environments to put together your workflows or data models and stuff. Usually, if you use a one-shop app builder environment, like Mendix, for example, you're going to get everything, right? It's going to have the GUI, it's going to have the domain logic, it's going to have the persistence, it's also going to have the deployment and the hosting, all rolled into one because that's really simple. The problem is you get somewhere really fast, but then over time it becomes harder and harder to maintain that stuff. So, what can non-programmers do, right? Usually when you build this application with a ready-made environment, you're going to end up with a CRUD-based application, right? They have data models, they all look like UML tables, you put them all together and it ends up being exactly what we don't want. And it's hurtful. You can't do proper versioning, refactoring is really hard. Team integration, like several people working on the same project, is really difficult. Debugging, observability. Some of these environments have integrations, some don't. You have to have some form of control over your data, right? So if you change your tables, you might want to take that historical data with you. You don't want to erase everything and start over. So that's also difficult. And the more visual the environment gets, the less possible integrations there are, right? So if you have specialized code that you would like to run with that, it's usually pretty hard. There's another kind of low-code applications called step functions. How many people use that? 1, 2? Okay. So step functions are actually a pretty good promise. They're supposed to be state machine as a service. They're all event-based, right? So really cool stuff. You push your events in, and it'll transition to the next state. It'll execute any function. It'll integrate with 200 different other services, and you don't have to write any code for it. Pretty powerful. Usually those events that we talk about aren't domain events, right? So at AWS, at least, events are always some message that's originated somewhere. It's not necessarily specialized. So you're going to end up plugging a lot of technical things together with a state machine that has the code that actually executes in Lambda functions, but the logic behind it, the business rules that govern that, are in your visual environment. It's pretty cool. You can do a lot of things with that. But all visual. How do you maintain that over time? How do you version that over time? Some of it, like you could write your step function with CDK. You can version that. But then your business logic is in the infrastructure code. As a rule of thumb, magic hides complexity, but it doesn't get rid of it. It's still there. You know how I know that? Code generators. Don't do that.